Hi everyone, welcome back to Learn with Pooja. Today we are going to discuss about different type of different distance matrices. Earlier sessions we discussed about text embeddings and how embedding models helpful to the RAG system and also in depth cosine similarity and formulas and how it will work and these things we discussed. So today we are going to discuss about a few more distance matrices. One of the main one is Euclidean distance. So Euclidean distance measures the straight line distance between vectors. So you can take that the a comma b is like a vectors as a summation of a minus b whole square root. So it is like a formula of Euclidean distance. So the characteristics is sensitive to vector magnitude and useful when vector length carries semantic meaning. However, modern transformer embeddings rarely encoded meaning in the magnitude. So we can see that dot product similarity. Dot product similarity is like a dot b. The advantage is like a faster computation work well if vectors are normalized beforehand. If product system vectors are often pre-normalized during indexing, allowing dot product to behave like a cosine similarity. Another distance matrix is like a Manhattan distance. So Manhattan distance measures the sum of absolute differences. So one of the formula is this is the formula you can ignore a dot b. This is the formula. A comma b is equals to sum of the absolute differences. So this is the formula of Manhattan distance. The characteristics of this Manhattan distance is like works well with the spur high dimensional vectors, less common with the dense transformer embeddings. We can do the simple comparison of similarity matrices. One is a cosine similarity, the strength is best for semantic similarity and weakness is slightly slower than dot product. Euclidean distance is good when magnitude matters, sensitive to document length. So, dot product is very fast in production, requires normalized vectors. Manhattan distance is efficient for spar vectors, rarely used for embeddings. So, these are like a different comparisons of similarity matrices. Best practice for RAG system. For modern transformer based embeddings, use cosine similarity as the default retrieval metric. Normalize vectors during indexing. Optionally use a dot product for faster computation. So in practice, over 95% of RAG system use cosine similarity for semantic retrieval. So, key takeaways from this comparison. Cosine similarity is ideal for RAG system because it focuses on semantic direction and it handles document with a different length and it work well with the transformer based embeddings. This makes cosine similarity the standard similarity metrics for semantic search and RAG pipeline. We can go now code level practical example. So import required packages for this similarity checks. So now one numpy is the one of the python numerical package like it is used for numerical operations and used for vector magnitude calculation, that is numpy link along import norm. And another one is a pandas used for creating and manipulating data tables, and OS and OpenAI is the OpenAI client library for accessing embedding model. Now take some chunks. So this is like a text chunks like the Great Fire on London in 1666 destroyed over 30,000 houses. So these are like three lines of text chunks. Define the user query question. Use user question is tell me something interesting about diseases in history. So to create a pandas data frame to store text chunks, this makes it easier to attach embeddings and perform analysis. So that's why we have taken as a list, and embedding df for data frame we are creating, and then defining the API client. The API key is the automatically read from the environment variable, because I exported. I have shown in the previous videos already, you can check it. And create an empty list to store embeddings. So optional helper list, so function to generate embeddings for a given text chunks. So create a embeddings method. Inside you can provide the text chunks along with the client. Call the OpenAI Embeddings API. Text embeddings 3 small. Yeah, I'm using this. You can use whatever you have. So I'm using this and converting text into a numerical vector. So client.embeddings.create from the OpenAI syntax, giving like input text chunk, and a model is a text embedding 3 small. So a text that needs to be converted to a vector, and the embeddings model used dot data to access the first result, and a dot embeddings like extract the actual embedding vectors. So you can return the embeddings and the embedding df and getting the embeddings from the chunks and apply. So now user question we are giving user question embedding, and create embeddings, and the text chunk is equal to user question and client we are providing. So I'm having like some issue, you can ignore, it will run for you if you install all packages. Now the second one is create an empty list to store cosine similarity scores now. So previously it's like a simple embedding we are using now. I'm sorry. Create an embedding empty list to store cosine similarity scores. So optional here, because we store similarity directly in the data frame later. So create a con same empty list, and define a function to calculate cosine similarity between two vectors. So calculate cosine similarity giving a text chunk embeddings and user question embeddings. So inside that, assign the embeddings to variable for easier reading. So A equals to text embeddings, embedding vector of a document or text chunk, and B is a user question embedding, embedding vector of the user question, and calculate cosine similarity. The formula is cosine similarity is we already discussed, per dot A dot B, and mod A into mod B. So dot product we are using, np dot here if you want to using numpy, np dot a comma b dot product of two vectors, and a norm a and norm b magnitude length of each vector. So cosine similarity is equals to np dot a comma b by norm a into norm b. So return the similarity score, return cosine. So apply the cosine similarity function to each embeddings in the data frame. The function compares every document embedding with the user's question embeddings. So here we are giving a embeddings df is a similarity and equals to the embeddings data frame, applying a calculate cosine similarity and user question embeddings and user question embeddings. So you can print this embedding df. The next part of the code is like importing a cosine similarity utility from sentence transformer, and this function provides an easy way to calculate cosine similarity between vectors. So from sentence transformer dot util import cosine sim, and convert the embedding calculate from the data frame into a list. So each element in this list is an embedding vector representing a document. So document embedding equals to embedding df, and embedding to creating like converting the to list. Store the query embedding. Here note is like normally this should be embedding of the user question. So giving query embedding is like embedding df and giving providing the embedding to list. So for doc embedding, loop through each document embedding and compute cosine similarity between the current document embedding and the query embedding. So consim is the written a similarity score showing how close the meaning are. So you can print and the score will show like this. So now the next one we are going to discuss about visualizing semantic relationship between text chunks using dimensional reduction techniques. So this is like a little bit lengthy topic we can discuss in the next video. So up to now we have discussed about like embeddings and in how to utilize this different type of similarity metrics and cosine similarity, Euclidean distance and Manhattan distance matrices, which is suitable for RAG system. We finalized like based on the comparisons, cosine similarity is one of the main for RAG systems for finding a semantic search. It's like a semantic meaning relationship. So now we are going to the next topic is like a visualizing semantic relationship between text chunks using dimensionality reduction techniques. Okay, have a nice day. We can meet next in the next video. Please subscribe my channel. Thank you.